So good morning, everyone. My name is Nadine Wael, and my group and I will be presenting our final thesis presentation, which is iAid, a smart assistive system. It will be presented by myself, Shahd, Mayada, Hazem, Adham, and Mohammed, and it's supervised by Dr. Seif. So this is the content we'll be covering today. We'll start off by a brief intro of what our project is about, and then we'll take each component and elaborate further on how we implemented it and the integration of all of them together. And finally, we'll talk about the challenges we faced throughout the project. So a brief intro of what our project is about and why we chose it in the first place. It's a smart assistive system for the blind and visually impaired, implemented by attaching a small webcam to your camera, to your glasses, aiming to solve the following problems. So first off, mobility. It's very hard for them to actually guide themselves from one place to another without the assistance of someone else or memorizing their way step by step. And they can easily trip and fall over something, especially if they're in an unfamiliar environment. Second off is unfamiliarity. It's very hard to instantly detect who they're talking to based only on their voice. So in 2020, there was a study conducted that showed that 237 million people worldwide are moderate or severely visually impaired, and the staggering amount of 1 million people blind in Egypt alone and 3 million visually impaired. So because we're targeting a huge population, we want our product to be very cost-friendly, easily accessible to everyone in every background, and easy to use in terms of UI, UX. And now Mohammed will further explain what our project is about.
Simply, our system has three main features: the facial recognition, accessible navigation, and real-time obstacle detection. The facial recognition feature helps the user to be able to recognize the people in front of them. And for the accessible navigation, this feature allows the user to navigate from some point or place to another independently without using others' help, while the real-time obstacle detection allows the user to be able to know if they are coming across an obstacle. And briefly, our system depends on a camera. This camera is connected to the mobile phones. And once it's connected, the user can open our app and use it to use one of our features, whether the facial recognition or the navigation and obstacle detection. We also need to mention that we created a survey and sent it to a group of people with vision impairment. And we depended on that to enhance our project. The main points we got that we have to make our system compatible with the most well-known operating systems for mobile phones, Android and iOS. We also learned that we have to provide our users to input their inputs, whether with speech or typing, especially that some users prefer to use typing in the noisy environment where the speech feature wouldn't be that effective. And since this is a project we are aiming to sell at the end, we came up with a business model canvas. And now I leave the floor to Mayada to start with the first feature.
The first feature of our product was facial recognition, and the model we're using is a pre-trained CNN-based face detection and recognition algorithm. It's an implementation of the open source face detection Python library, and it has an accuracy of 99.38% on the labeled faces in the wild benchmark. Our model offers accuracy, computational efficiency, and extendability, and our model architecture is as follows. The first step is facial detection using the histogram of gradients, in which every pixel in our image is analyzed with the pixels directly surrounding it. And by doing this, we compare the intensity or the direction in which the picture goes from light to dark, and arrows are then drawn. Those arrows represent the gradient, and by doing this for every single pixel, we're generating a hawk pattern, which is then used to detect faces by comparing it to a hawk pattern that was already generated from our training faces. Next is the posing and projection of faces by distortion, in which we use the face landmark elimination to extract the basic features that are found in every face, such as the inner corner of your eye, the edge of your eyebrows, your chin, and so on. Next is facial encoding using a pre-trained CNN model, and this extracts 128 measurements found in the image. And this ensures accuracy because no matter the picture, if it's the same face, CNN will generate almost the same measurements. Finally, we match the face to a name by the SVM classifier, and then we send this name to Google Translate's API to read it out. And this was done based on the fact that based on our survey, people prefer to hear it. This is a demo from how it looks like from our laptop. If a person were to step in front of the camera, the name will be shown and it will be read out by Google Translate.
Hazem.
And if this person was unknown, it would say unknown. Next, Hazem and Nadine will be presenting about obstacle detection.
Okay, so now I'm going to be talking about obstacle detection and how we implemented that model. So firstly, we wanted to create a system that emphasizes performance while also maintaining a high accuracy. So to make it more convenient to the users, we opted to make a single camera system as opposed to lots of things we found in the references and literature survey, since most of them used either a stereo camera system or a sensor system. But we wanted to minimize hardware components to make it more convenient and more accessible to the users. So we used a single camera system, and we opted to use computer vision algorithms, which would be faster than using AI models, since it is a real-time system, and the speed and efficiency would also be recommended. So since we cannot estimate depth from a single camera system, our approach was based on capturing consecutive frames, and then we track the motion of objects between each frame and the consecutive frame, and finally estimating a collision time between the two frames in the video stream. So this is an overview of our architecture. As an input, we take the video stream and then we process throughout all these points, and then we finally give out an output of a warning of a potential obstacle. So, and then going to talk about each point individually. So firstly, we take a video stream, and that video stream is then input into an image descriptor. That image descriptor gives us points on the dataset. These points are then split into two types of points. The first type of points is an irregular point dataset, and the second is a regular points dataset. So the irregular points dataset is done using the texture itself of the frame. So it helps us recognize irregularities, and also it helps us find out like places and corners using a corner detection algorithm. The corners itself help us define an object. For example, we can see here that it determined the edges of the wall of the clock itself as an object. For a regular points dataset, we determined that the area that we need to most focus on is the area directly in front of the user, since that is the area that the user would be walking in, and most likely there would be more obstacles. So therefore, we opted to take more points in that area so that it would be safer, and we'd compute this area more. And then we compute local and global displacement for the frames and for each point that we extracted in the frame. So as we can see here, we compare each point on the first frame to the second frame, and then we track the points with their corresponding points in the second frame. As we can see here, if you track any of the lines, you see that it starts off at a single point, and then it tracks it to its corresponding points on the next frame. And then we compute the optical flow or the motion vector of each point to estimate the velocity of the point and how it's moving. As we can see here, it's tracking the points on Nadine's face and following it, drawing the lines throughout the frames. We can also see that as the camera itself shifts, the lines are then drawn so that either if an object is moving or if the camera itself as a whole is moving, it will also be able to recognize that entire shift. But however, we do not want the moving of the camera horizontally or shifting of the head of the user to be an obstacle or to be misinterpreted as an obstacle approaching us. So therefore, we would need to estimate or calculate a homography matrix. That homography matrix is basically the global transformation of the entire frame itself. So therefore, each frames would then be as close as possible, and only things that would be actually changing would be the objects itself in the frame and not the entire shifting of the frame. So therefore, this allows us to estimate the background motion of the camera itself, and the images in the background that are moving would simply be ignored, and we'd also be able to focus on the points itself in the foreground. So then to classify which exact points are in the foreground and choose which points to ignore in the background, since we also chose to do that to save computations instead of computing the entire data set of points, we just focus on the points in the foreground itself. So we calculate an error value. That error value is basically the vector of the second points, which are computed from the second frame. And then we subtract the homography itself, the homography multiplication by the first frame, so that therefore both frames would be equal, and we get an error value. That error value would then represent the motion of the point itself, and it would be ignoring the entire motion of the entire frame. So therefore, points with a high error value means that the point itself is the one that's moving and not the entire frame that's shifting. So therefore, these are the points that are moving rapidly, and these are the points closer to the user, and therefore these are points to be focused upon. And then Nadine will be continuing on how we chose to determine what are obstacles in our dataset.
Okay, so after calculating the foreground points, we calculate the time to contact for each foreground point. Okay, so how is this time to contact calculated? It's calculated based on the change of the y coordinate when the user is heading towards the focus of expansion point of the object itself and the optical flow output. However, the x coordinate doesn't really affect our time to contact metric because, as Hazem mentioned earlier, we do not want to consider if the object is moving horizontally. We want to consider when the user is moving towards the object itself. Therefore, the time to contact is calculated by dividing the y coordinate of the object over the velocity of the object, which is the optical flow output as mentioned before. Next off, we implemented a k-nearest neighbor classification where we set the number of neighbors to be considered by the KNN algorithm using parameter tuning. And this uses proximity and similarity to make classifications about the grouping of an individual foreground point to another individual foreground point. Then we implemented clustering, where each cluster of the foreground point represents a single entity at first, and then the closest two clusters are then joined together until it iterates all over the foreground points to reach our predefined tree height. Why did we do these 2 points? First of all, the classification helps in time because it's very fast to process a group of coordinates, not each coordinate itself, and it's very accurate in terms of the results. Second off is clustering. So after you cluster, each cluster represents the obstacle that will be detected by the user when he is using the obstacle detection program. So we calculate lastly the TTC average, where each cluster is an obstacle for the user, and when it reaches a certain threshold, it starts to make a beeping sound so that it can alert the user that there is an obstacle in front of them that they need to take care of. And this is a demo of me trying it out at home. ما فيش صوت. Okay, so as you can see, when I go closer to the vase, that starts to beep. So the blue and the green colors are the clusters. And lastly, when I go towards these chairs, it groups them as a cluster and an obstacle is detected and it makes a sound for me. Okay, next, Shahd will be presenting the navigation feature.
Okay, so now I'll talk about the navigation feature, which is one of the main features of our system. For the navigation, we use Google APIs to get the location of the user in real time and to display the map inside the application. Also, it provided us with autocomplete suggestions for the location search. And lastly, we integrated an app launcher to start the directions toward the desired location. And the mode was set automatically to walking. Moving to the integration part, in which I will show how we integrated all the features of the application together. I will start by how we integrated the camera. This is the camera we are using. It's called Lily Go camera, and it has a wider angle lens. It works with a C code that sets up an HTTP server for video streaming. And then we use virtual camera for taking this video streaming and taking this video into our Python code, because the Python code requires RTSP streaming. Now Adham will elaborate more on the integration part.
So now that we have all of our features, so we wanted to put them all in our application. So what we did was we had a server run these algorithms, and our phone itself will open WebSockets with this server so we can communicate back and forth. Everything is communicated through just simple strings. We just take, for image recognition or obstacle detection, we just take one image or a lot of images in a row. We just convert them to a binary encoding. So binary, byte encoding, so just a string, and I send it to the server, so it's very quick because it's just a string. And on the other side of the server, it decodes this byte to a picture again, so we can do all of the algorithms we mentioned before. So after that, our application itself, so application has all of our features, the only thing the user can use. So we can enable or disable facial recognition and obstacle detection, because we're gonna use it. For facial recognition, we can we want to add a new face. So I recognize someone new. So we're either gonna upload an image from my gallery, or we're gonna take a picture and send it. So both of these can be done from the app. And finally, the application itself is what communicates with the servers to send inputs and outputs. So of course we had to make some interface requirements, because we're making this app for the visually impaired. Not all of them are blind, so we had to make interface requirements. So first of all, the design had to be very simplistic. We don't want any animations, anything unnecessary. We're using enlarged text, and we're not dependent on colors to give out any information, because in case of color blindness, for example. And another thing is every button, everything in the app has to be labeled for the user to be able, for the screen recorder to be able to see it. So what a screen recorder is, most of our phones, Samsung and iPhone, Android and whatever, have a screen recorder to be able to read whatever is on the phone. So the user can know what this button is and then press on it and use it if necessary. So everything has to be labeled. We're not using any icons, anything like that. So here's a demo of adding a new face.
Upload. Button. Detected. Icon camera. Camera. Take picture. Button.
So this is using the camera to add a new face.
Okay. Button. Thesis.
The thing that's talking is the screen recorder.
Alert.
Yeah.
Edit box. Voice input button. Windows Samsung keyboard.
Mayada.
Mic button. A replaced air. Done. Mayada. Edit box. Send. Hide.
So now we're gonna try to detect Mayada now that we added her.
Mayada.
And now we're trying to detect someone unknown.
Unknown.
Okay, so this was demo for the facial recognition. So over here we can detect the person in front of us. If we have them, if we have added them, we're gonna say their name out loud. If not, it's gonna be unknown and add faces just from the gallery or the camera. And another demo for the navigation after implemented on the phone.
Google Map. Search location. Editing. Edit box. Search. Voice input button window Samsung keyboard.
0.90.
0.90 mil, American University New Cairo 1, Egypt, window B. 0.90 mil, American University New Cairo 1, Egypt. Get directions. Open with. Maps, column 1 in grid, 1 row, 2 columns. Maps. Map bearing 258 degrees button.
So this is just the navigation demo. So we tried in the demo to use everything using voice activation, so we can able to show off the features. And now for future improvement, Shahd will continue.
So now for the future improvements, we have two main goals we need to work on. First of all, while integrating the camera, we faced a challenge, which was that the Python code did not, it needs an RTSP stream, and our C code does not provide this. So we managed to have two solutions. The first one is to convert the stream to RTSP. However, this solution was time consuming and was complex. So we chose to use virtual camera, which was an easier option. By this option, we took the video streaming and converted it to a virtual camera, which is then detected by the device as a webcam. The second part is the second challenge we encountered is while integrating the features in the app was that the Flutter app does not support Python, but all our features run on Python. So although it has some Python packages available, most of them do not support C extensions, which we rely on in our algorithms. So this made it difficult to stick to our initial plan, which was running all the processing inside the application. So we had to choose to using WebSockets to connect between the application and the server. This worked effectively with the facial recognition because it needed only one frame. However, with the obstacle detection, there was some delay because it needed more frames per second. So this was the problem, and we are planning to solve it in the future by having a new application running on Python. By this, we can stick to our initial plan, which was having the application as our main processor without needing a server. So thank you for your attention.